The universe had a beginning. 14 billion years ago, everything that exists erupted from a point smaller than an atom. But how does it end? Scientists have mapped out every possible fate, from the Big Freeze, where every star burns out and the cosmos goes dark, to the Big Rip, where dark energy tears apart every atom. And thanks to new data, one scenario is now looking more likely than the others. The universe began 13.8 billion years ago in an event we call the Big Bang. Everything we can see, every galaxy, star, planet, and atom, traces back to that first fraction of a second. But beginnings imply endings. And for decades, cosmologists have been asking one of the most profound questions in science. How does the universe end? There is no single answer. Instead, physics offers several possible fates, each more strange and unsettling than the last. From a universe that freezes into eternal emptiness to one that tears itself apart at the atomic level, the ending depends on forces we are only now beginning to measure. And recent data suggests one scenario is pulling ahead. The most widely predicted fate of the universe is the Big Freeze, also called heat death. In this scenario, the universe continues expanding forever. Stars burn through their fuel and die one by one. Galaxies go dark. Black holes slowly evaporate through Hawking radiation over timescales so vast they make the current age of the universe seem like a blink. Eventually, the last particles drift apart in an infinite, cold, dark void. No structures, no energy gradients, no possibility of anything happening ever again. The temperature of the universe asymptotically approaches absolute zero. This is the thermodynamic end state, maximum entropy, minimum information. It is not a dramatic ending. It is the quiet cessation of everything. If the expansion of the universe slows down enough, gravity could eventually win. Everything that flew apart in the Big Bang would begin falling back together, galaxies merging, space contracting, temperatures rising. The universe would compress into an increasingly hot, dense state, ultimately collapsing back into a singularity, the reverse of the Big Bang, called the Big Crunch. For most of the 20th century, this was considered one of the most likely scenarios. Then, in 1998, the discovery that the expansion is accelerating seemed to rule it out entirely. But recent Decay data suggesting dark energy is weakening has quietly reopened the door. If dark energy continues to fade, the Big Crunch is back on the table. In 2003, physicist Robert Caldwell proposed a scenario far more violent than either freeze or crunch. If dark energy does not just remain constant, but actually strengthens over time, a form called phantom energy, the expansion of the universe would accelerate without limit. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets, then atoms themselves. In the final fraction of a second, the very fabric of space-time would rip apart. This is the Big Rip. Current observations do not favor phantom energy. If anything, dark energy appears to be weakening, not strengthening. But we cannot rule it out entirely. The Big Rip remains one of the most terrifying possibilities physics has ever produced. Some physicists have proposed that the universe does not end at all. Instead, it cycles. The Big Bounce hypothesis suggests that our Big Bang was not the beginning. It was a transition. A previous universe contracted, reached a point of maximum density, and bounced back into expansion. If this is true, the universe has no beginning and no end, only an eternal sequence of expansion and contraction. Loop quantum gravity, a leading candidate for quantum theory of gravity, provides a mathematical framework in which this could work. The singularity at the center of a Big Crunch is replaced by a bounce. Some models suggest each cycle produces slightly different physical constants, meaning each universe in the sequence would look different from the one before it. Perhaps the most unsettling scenario involves no gradual process at all. Quantum field theory suggests that the vacuum of space may not be in its lowest energy state. It may be in a metastable state, like a ball, perched on a ledge rather than resting on the ground floor. If so, a random quantum fluctuation anywhere in the universe could trigger a phase transition. A bubble of true vacuum would form and expand outward at the speed of light, fundamentally rewriting the laws of physics inside it. Every particle, every force, every structure would be replaced by something entirely different. There would be no warning, no possibility of escape, and no way to predict when or where it might happen. We would simply cease to exist, replaced by a universe with different rules. As of 2026, the most likely fate of the universe is still the Big Freeze, but with an important asterisk. The DZ Dark Energy Survey and upcoming results from the Euclid Telescope and Rubin Observatory may shift the balance. If dark energy is truly weakening, scenarios involving eventual contraction, the Big Crunch or the Big Bounce, become more plausible. If dark energy is constant, the Big Freeze wins. If it strengthens, the Big Rip is possible. Vacuum decay hangs over all scenarios as a wild card. It could happen at any time, regardless of what dark energy does. The honest answer is that we do not yet know how the universe ends. But for the first time, we have the instruments to find out.